My name is Jérémie Galarneau, and I'm the head of support at EfficiOS. I'm the maintainer of the Babel Trace and LTTNG tools project. And just to run you through the projects that I maintain, the LTTNG tools, if you know a bit about what LTTNG is, it's the session configuration daemon, it's the network streaming daemon, so the server collects the traces when you stream them over the network, and the command line interface to LTTNG. And Babel Trace is the command line interface pretty printer to read the traces. It provides the CTF writer library, which is used by Perf to convert to CTF. And the Python bindings that you can use to write your script. And what I'm going to present today is mostly based on that. Previous talks about LTTNG have mostly focused on the internals, how we made it scale like it does right now, how we've reduced the per event cost. And today, I'm not going to go into the internals of the tracers themselves. I really want to focus on how the traces are actually collected in the real world and what you can do with them. So why you should trace? LTTNG has two tracers, one user space and kernel space, which are used to correlate traces amongst themselves. And so you can see how user space is interacting with the kernel and vice versa. And for a long time, those two tracers have corresponded to two distinct user groups that didn't have that much overlap. On the user space front, you have people using open source projects that are already instrumented. Those would be Node.js, CoreCLR, QEMU, and a few others. But most users are actually using LTTNG UST with closed source applications. And they're all what they're actually developing. And it's often used as a flexible high-speed logger. So people benefit from filtering, the trace streaming, snapshot modes, and all that stuff that LTTNG does. And on the kernel side, you really add users that are kernel experts, people who develop drivers, people who are looking for race conditions and those kind of things, and there's not a lot of overlap between the two. And the perception has long been that the kernel space tracer is only useful to kernel developers. Hopefully this is going to change your mind. And do we need tools? Well, yes, because the traces are huge. LTTNG, as far as the kernel tracer is concerned, is collecting very fine-grained events, as you may know. Things like the block layer events, scheduling events, RQ, net power, syscalls. Syscalls are going to make sense to your average application developer, but the rest kind of requires you to know about the kernel internals. And so manual inspection is going to work if you know what you're looking for, but at some point you really need tools to at least eliminate most of the traces and allow you to focus on what's actually interesting. So we need those tools. And basically, at the beginning, we noticed that the user space users, or people using the user space tracer, were the first to build tools that we really saw in the wild. But those tools were text-based. People were piping hundreds of gigabytes of traces through Perl, Awk, Sed, and coming up with those huge one-liners that were useful to them, but they were most of the time unmaintainable, unmanageable, and they were shuffled around. And they would break when people would add fields to their traces, regex would not match anymore. So when I started working on the LTTNG project, the first thing I did is introduce the Python bindings to read traces around 2013. And really the goal was to let those users come up with something, hack something together to parse the traces, look for patterns in debugging and testing scenarios. And it's still reasonably efficient in most scenarios, and the scripts can be maintained as internal tools. But the thing is, we wondered in 2014, could we do the same for kernel space? And this is the piece of infrastructure that we at EfficiOS know, because we don't know your user space stack. So we developed a collection of utils that allow you to model some kernel space, kernel subsystems, and allow you to track their state. And you can see statistics about latency of RQ, IO scheduling. I'm not going to touch too much on RQ today because this is less relevant for DevOps. A system called latencies and top resource users, whether that be CPU or IO. Those scripts are all open source. You can find them on GitHub. So those scripts, that's what they look like, and I'm going to use them to debug real-world scenarios today. This is CPU top, so you can capture a trace, run that on the trace, and see which were the highest CPU users during that time. This was connected on my laptop just before, so you can see that watch was actually consuming the most CPU, but all in all, the machine is fairly idle. You can restrict that to a given time range, and you're going to see how powerful that is later on. The same for I/O usage stop. You can see at the syscall layer the reads and writes that are done, but also at the block layer and then at the device layer. So you can see which read actually triggered something on the block layer. And syscall statistics. So you can see which syscalls were used and what were the returns. So that's good for basically understanding the error rates of your application. And again, that's one of the most powerful tools that we have right now. It's the frequency distribution. And that allows you to figure out if there are outliers in your trace, and if that's what is actually slowing down your workload. Everything I'm going to show today is integrated in Trace Compass, so if you don't feel like using the command line, you can do everything that I'm going to do in the user space, in the UI of Trace Compass. So the principles, we do two things in LTVG analysis. We track resources and we track durations, latencies. And the principle is very simple. You follow in the trace what a given TID is doing. You see it being scheduled on the CPU tree here. You see it opening a file, and then you can map FT22 back to that file. Pretty simple. And you can track latencies. So you're going to see a syscall entry read, a number of things, and then syscall exit read, and you're going to know the duration. Fairly simple. The realization we had in the last month or so is that basically all of that could be generalized and made useful to people tracing their user space application and the kernel at the same time. And so you can define your own periods now. To use the same example with the read, that would correspond to defining a period as starting at the entry read and ending at the exit read event. And you can capture a number of things. So to give an example, if you had a user space application that is processing a job, you would see, well, the job itself, the boundaries. So you always need a hook in the trace to know where to start and where to end the job. And you can break down that period by sub-period. The same applies to the kernel, by the way. So what I'm going to tackle are some real problems. I actually deployed a WordPress instance that is separate from another MariaDB or MySQL instance. Both of those are communicating with each other to serve the pages. And we're going to see why we have such long time to first byte. We don't worry about what's happening in the browser today. Really, the stack doesn't matter. It's just an example to show you how we can understand what's going on, even though we have no user space implementation. And we're using very generic scripts. So the first thing I did is trying to figure out the anatomy of a request. And I've never looked at the HTTP code, or MySQL for that matter. We basically define a request as the time between the accept system call returning and the close associated with that FD. That gives us the larger request. And inside that, we can define the URL rewrite phase. The same for the DB queries. We see the connection happening to the database server. We say that PHP resumes execution. And so we're just trying to have a coarse breakdown of periods. The goal is not to benchmark. The measurements are not going to be precise because I'm just looking on syscalls and those kind of events. And I don't know what the application is actually doing. We just want to know in which phase of processing the problem happened. That's the goal. So for the rest of the demo, you're going to see a request being defined as those subroutines. The way I deployed LTTNG, and we've seen a lot of users do something similar to that, is to create a session profile with a list of events that you want to have enabled. You can do that on your laptop, and then you just SCP that file down to your nodes, load that with LTTNG. That's going to be LTTNG load my profile. And you can stream your traces down to a collector node using the relay daemon. The relay daemon runs on OS X, Linux, pretty much every BSD out there. So the first case is a case where every request is unacceptably slow and doesn't meet our QoS that we've defined. There's no connectivity problem. That's all happening locally, so we're just removing a bit of unknowns here. We capture a trace for a couple of seconds on both nodes. We stream them to my machine, so you don't need to. You never touch the disk on the nodes if you stream over the network. So you don't need to provision any space on the actual nodes. Although local buffering could be used if you don't want to use too much network bandwidth. And there's never any pushback against the kernel. So we don't slow the applications or the kernel just because you can't cope with the amount of tracing data. So once I have my trace, I can actually look at the top requests using the util LTTNG period log. You have the period top. You get the top requests. And this is going to give you a breakdown like that. Not that this util doesn't know anything about my stack or whatever is happening. So I have a request, the time it started, the time it ended, and the duration. Now what I can do is rerun it with the top requests, a breakdown of frequency, and general stats about those requests. So you can see here that everything is pretty slow. They're all over, pretty much all over 3 seconds long. So we don't have any outliers. Everything is slow. And if I look, those are all the requests that happened during that time. Still have the top durations here. So, okay, that doesn't tell me a lot about the system, just tells me that it's slow, which I already know. I can then run LTTNG CPU top, just to figure out over that trace who was using the most CPU. And what we see here is that we have a whole lot of Apache workers. They're all separate processes here. All taking around 2% CPU time, so that shouldn't be a problem, except that this is running on one CPU machine. So that machine is obviously overcommitted. Fair enough. This is not a use case where a tracer is the best tool. And I'm going to be honest, not because I developed one that I'm going to say that it's good for everything. Pretty much any monitoring tool would have told you that. You look at HTOP, okay, that machine, I'm not expecting it to be loaded that much. So. And it's not really an efficient way to calculate CPU usage, let's be honest. So most monitoring tools focus on trends and averages and would have given you a big picture view of that. And my nodes are all overloaded. I need to provision better machines or more machines or what have you. And they're going to give you error rates. Tracers are great, any tracer really, to figure out usage problems. I have a process that's emitting all those small reads all the time, or figuring out the race condition, those kind of things. What I'm going to focus now on is spurious issues, things that happen once in a million times. And for that, I'm going to use the snapshot. And what snapshot mode is internally, the people develop LTTNG, we all call that a flight recorder mode in retrospect. But it's basically tracing all the time to memory buffers, never touching the disk. So it's very low overhead. You can configure your buffer size, so if you can't afford to provision too much memory or RAM for tracing, you can reduce that footprint. If you have enough memory, you can go crazy with that. And whenever something unexpected happens, you can take a snapshot. And that snapshot, in this case, can be even saved to disk or streamed over the network without ever touching the disk again. And this is what I'm going to do. I've developed a proof of concept Apache module. Sorry, that is actually inspired by mod log slow. And what mod log slow does is you give it a threshold over which any requests that take over a second, let's say, are going to be logged, which is fine. But I actually want to trigger a snapshot on all the machines that are involved with that request and perform a number of analysis on that. Limitations, because I've made the code open out there, don't use that in production. I mean, it was developed really quickly for that demo. I'm just SSHing into the targets and taking a snapshot. This can take a long time, so you might have overridden your buffers all the way and lost what actually happened during that request that way. And there's no rate limiting, so if you're just on the verge of exceeding your QoS, then taking a snapshot could trigger a number of other snapshots and go into a feedback loop. So really, proof of concept, not use that. So case number 2. We have a session profile loaded, so we have tracing enabled. That can be running for days and days and days, no problem. I have LTTNG read AD on my machine, and I'm going to wait until a request fails to meet the 1 second per request rule I've defined. And we'll see what happens. So I actually left that running for a while, and I was basically stress testing the server. And at some point, I noticed that I had a couple of snapshots on my laptop. So we can look at the request log again. This is the same command line we used previously. And you can see here that pretty much everything is under control, except the 6 requests or so, 8 requests that we have here that have failed to meet our quality of service standards. Okay, so we'll try to figure that one out. You have the tops here, and they're all over a second. Okay, Kernel. So if I run LTTNG CPU top, just to see the top 50 CPU users during that time, well, Apache is doing a job. There's no spike, so okay. But then you can actually go back to your request log, take the longest one here, copy paste that that time range down into CPU top, and that gives you pretty much this command line here. And now we see that during just that request, we had XZ consuming around 40% CPU time. So that's unexpected. If I look at the top I/O usage top I/O users, I'm going to see XZ, which is actually reading dmessage.log. So we're kind of starting to understand what's going on here. And if you use that in Trace Compass, you're going to see pretty quickly that Bash is actually launching XZ, and it's doing so after having execved a file, which is called logcollect.sh. logcollect.sh. So we're collecting logs on the production machine, compressing them, and that's throwing off our numbers. Case closed. So in the third case, same thing, I'm leaving my machine running for a while, and I've noticed a couple of snapshots in there. So I always start looking at the request log, and we can see that during the time that this snapshot covers, we only have 2 requests that were around 5 seconds long, and 4 that took very little time. So, okay. Let's try to figure out what was going on at that time. We can look at the top CPU users during the longer request, and nothing's out of the ordinary, so, okay. Maybe I/O, nothing there. I mean, landscape, doing a bit of I/O, but not unexpected. Session D, but it's probably not a problem to have done 62 Ks during 5 seconds. Fair enough. So I have nothing interesting in the IO usage log. Now if I look at the syscall stats for Apache, the culprit is pretty clearly a long select at max 5 seconds. Pretty close to the total request time. So, okay. Is there anything we can do with that? Well, if we use trace compass, at that point, we have to look at the actual events in the trace. This is as far as the analysis are going to allow us to eliminate stuff. But once we're in trace compass, we can see that we're accessing, well, Apache is accessing a plugin named hello.php. And it's actually creating a socket in UDP mode. And using connect in the case of the UDP socket is just going to set the default destination address to 8866. So I know 8844, 8888, 8866 is kind of weird. If I look at the code of that WordPress plugin, we're seeing that it does its own DNS resolving. And someone probably copy-pasted that line and figured out that 8866 should work. Case closed. So another one that would leave you scratching your head, or at least mine. Hopefully you're not scratching my head. We have everything is going fine on that server, and we have 75 requests that fallen under that first bucket, which is well within a reasonable range for what we expect of that system. However, we have this request that took 2 seconds, about that time. If I look at the top, I have 2 requests in that snapshot that actually failed to meet our quality of service standards. Okay, fair enough. So again, I'm going to introduce a new tool. If you remember the way I broke down a request, I'm actually going to use that with LTTNG period top. And I'm sorry for the length of the command line here. But what you're actually seeing is, I'm going to use the mouse, but the URL rewrite period being defined with the begin and end expressions. The same for before DB connect, and the request is its parent. Then DB queries, rendering, and I figure out that the rest is going to be the time it takes to send it back to the client. In our case, that's very little time, so we don't really care about that. The nice thing is that we can aggregate those periods inside their parent and group by worker PID. And we know that under this configuration, Apache is never actually serving 2 requests on the same PID at the same time. So making our job a bit easier. And you can see here hopefully you can read, but the request is broken down. So go a bit down. Any URL rewrite before DB connect, URL rewrite before DB connect. So those are requests that don't match our pattern, which is fair enough. If I look at the actual long request that I had, I'm going to take its beginning timestamp and search for that. And I see that most of the time is spent in the DB queries. So it's good enough that we have eliminated the Apache server from the equation. That's just what we want. There's no measuring performance here, or at least not precisely. So let's look at what's going on the DB itself. Okay, over the duration of the snapshot, not a whole lot's happening on the CPU side. So we're still in the dark. But if we look at the CPU usage during the longer request, we can see that something called my service was taking 20% of the CPU time. Fairly high, but I mean, it shouldn't be a problem. Now, if I look at the I/O usage during that long request, again, same idea, you just use the same time range with I/O usage, or I/O usage done. We don't see anything, really. What you're going to see is actually at the block layer level, and we see that K-worker here is actually writing 230 megabytes during those 2 seconds. Kind of unexpected, right? Now, this is another point where tools are leaving us to our own device, and we're going to have to look at the trace. But at least we know where to look for. And if I go in Trace Compass to the beginning of the activity on the My Service process, we actually see a print K event. And that process is crashing. This is what's happening. So the process is crashing, and K-worker is working with the process to extract the core down. The limitations, the reason why we can't really associate right now the I/O activity that occurs because of the crash dump and the My Service process is because we, well, tracking I/O at the block layer is really hard. Because at that point, there's a fuzzy matching between the actual processes and what's happening. And there's obviously no open syscall because that's all happening in the kernel. Because everything we've seen so far was based on syscalls, now we're actually using kernel events that have nothing to do with the user space. And block 30 buffer is happening in the context of the crashing My Service, but what we actually use is block RQ issue and block RQ complete to do the accounting on the block layer side. And that happens in the context of K-worker 02. So there's still a lot to be done on that front, but hopefully I've convinced you that manual inspection is not the entry point anymore when you investigate a trace. You don't need to be a kernel developer to make sense of what's happening. And it's almost automated. If you deploy LTNG and you have a relay daemon, you can collect your traces and completely forget about what's running on the actual nodes themselves. And just focus on analyzing your snapshots, perhaps even running LTNG analysis on them in advance. And then you know where you can break down and really start working on the investigation. So, thanks a lot. Any questions?
So you said this wasn't designed for benchmarking, so I can't say I want to use it in conjunction.
So it depends on how precisely defined your queries are. If you really know that what's going to happen is between open and a read, it's going to be as precise as you can get. The thing here is that I know nothing of the internals of Apache. So I'm looking at the trace and kind of deducing what's happening. In the case of Apache, I see it statting PHP files, which is already has cached. So I'm kind of figuring out where it's ending up the code to the actual PHP interpreter. But I wouldn't use that to finally measure any performance. Yes?
Do you have any good recipes for getting around the scenario where we're snapshotting at heading over our quality of service threshold? But as often as not, the reason there is a little bit ahead.
Yeah. If it's too far ahead or in the past, you're basically going to lose the information, right? Because you have overwritten your buffers. that's why the sizes are configurable. So if you know that you tend to have that kind of situation, you can use larger buffers. Or you can have multiple sessions in LTTNG running at the same time. So you could have a long running trace and use the trace file rotation to actually use the disk and keep a very long buffer of things that happened before that. So it's very flexible in that respect. Cool. All right. Nice.